Title of my talk is Mastering Kafka at Scale, Unleashing the Power of Temporal at Stripe. Basically just going to go through how we use Temporal to manage all of our Kafka clusters at Stripe. So just a little bit of an outline of what I'm going to go over in this talk. I'm going to start by just giving a little bit of insight into our streaming infrastructure setup at Stripe so that you can understand the complexity and all of the different components that we use to run Kafka. Next, I'll introduce the control plane and talk briefly about what it is. Next, I'll dive into some specific workflows that really are good use cases for Temporal. Specifically, I'll talk about our archive monitor workflow, which we use to make sure that all of our data is archived into S3 correctly. Our replace broker workflow, which we use on a regular cadence to replace both unhealthy brokers and brokers that are out of host lifecycle compliance, which I'll talk a little about later. And then lastly, I'll also talk about the Kafka planner workflow, which is the workflow we use to make sure that all our brokers and clusters are operating healthily all the time. Next, I'll go into two techniques that we use to make sure that our workflows don't basically work against each other and apply multiple operations to a cluster at once. So something that we're currently working on is something called workflow coordination. It's actually a project that I'm currently working on right now. And I'll also talk about a safety barrier, which is something we use to make sure that operations, harmful operations, aren't applied prematurely to clusters when they're not ready for it or don't want that operation to be applied. Then I'll finish with some closing thoughts. For example, why we like Temporal and what we learned along the way, specifically what I've learned. So just to give an overview of our infrastructure setup, we have 50 Kafka clusters that span across 3 environments and 4 different AWS regions. So yeah, a lot of infrastructure that a team of 6 people have to manage, given that we host our own clusters. In front of that, for most of our clusters, we have this routing layer called kproxy. And there's another talk online from one of my teammates that was given at the Kafka Summit, I believe, 2 years ago, if you're interested in that. But the long story short is that we use this routing layer to ensure that we have high availability for our clusters. And you can kind of understand why this would be important for a company like Stripe, which is constantly processing payments. We don't want our Kafka clusters to go down because then payments, CDC, the whole shebang, we start having problems. Next, we have our Kafka archiver, which we use to take the data from our brokers and then put it into S3. So like you can imagine, we don't have infinite retention on our brokers, but basically when it goes to S3, for the most part, we don't really delete that data. Yeah, we don't really delete that data. And, another use case would be, so most people actually just use Kafka to write their data to S3, which I'm assuming most of you know this and have similar use cases at your own companies. But typically on the consumption side, we'll also have users like Flink teams, which are using it for things like Kafka sources, and then I believe that we have some ML teams that use Kafka topics in order to constantly process data into things like fraud detection. Kafka cluster management, we do use the control plane, but we use something else as well. So at the core, we have our Kafka clusters, which they run Kafka. And on top of that, we have Temporal as an interface, which we use to interact with our clusters and apply operations. So the most frequent types of operations that we have are run automatically through the control plane. And this is going to be the Kafka planner workflow, which I'll talk about later. We'll run these operations on our clusters. So Temporal does 2 things. It acts as an interface for users as well as to apply operations automatically. So like I just kind of alluded to, a user could also use this CLI that we've developed, that we've exposed to admin boxes to apply operations to clusters. So that's another way that you can apply an operation. And then lastly, we have this other thing called Tenson. And it's an internal tool that was developed by the deploy team at Stripe. But what we use it for is we use it to, it's a new feature that we've developed for our team to automatically go ahead and apply new Kafka configurations to all of our clusters, as well as install Kafka binaries onto our brokers. So the major takeaway I want you to take from this slide is that there's a lot of different like agents within our system that can apply operations to the clusters. We can either have it automatically applied by Temporal or our control plane. Users can apply them, and also Henson can apply them. And in particular, for just Henson in general, the only operation that they'll ever apply to a cluster is going to be a rolling restart. So imagine, for example, recently, like one of the configurations that I had to change in our clusters is we wanted to have like inter-broker TLS communication between like all the brokers in our cluster. Like in order for that change to be picked up, we need to run a rolling restart on it. So every single time you run a deployment for one of these Henson deployments on a cluster, you need to have a rolling restart happen. So yeah, you can see how this can be problematic because like you wouldn't necessarily want to have a rolling restart happen at the same time as a broker replacement. So enter the Kafka control plane. And so what does this do? I've talked about this a little bit already, but it just has a lot of different workflows that it runs to manage our clusters across Stripe. So like I said, the Kafka planner workflow is this workflow that we run on a 15-minute cadence. And what it does is it goes through and it checks to make sure that each of our clusters are healthy. And then if there's some sort of issue, for example, a cluster needs to be rebalanced, it will then execute a rebalance. We have our replace broker workflow that we use to replace brokers. Pretty simple. Well, I mean, at the surface level, it seems pretty simple. It gets a little more complicated when you're using EBS volumes, but that's another workflow that we probably run the most. We have our rebalance Kafka cluster workflow, which just uses cruise control under the hood. It just basically makes an API call to cruise control to rebalance the cluster. We have our rolling restart workflow, which we use to restart the clusters the brokers within the cluster one by one. I won't talk that much about this workflow, but this is actually a pretty useful workflow to use with temporal and durable execution because, for example, like let's say that you have like a 42 broker cluster, which is a pretty standard size that we have at Stripe. Let's say you've gone through 20 of your brokers, then all of a sudden there's some sort of network issue, you have a deployment that goes on, and like the workflow, there's some sort of failure within an activity. It's useful to be able to store that state of which broker you're on during that entire workflow, so that you don't actually have to start the rolling restart from scratch, and you can just start right from where you left off, from the broker that you left off on, and then continue. We have something called the topic differ workflow, and this is kind of like some slang that we have for managing all of our topic configurations. We run this within each of our regions. Then we have our archive monitor workflow, which I mentioned earlier, and yeah, like I said, this just ensures that all the data that we write to S3 from our Kafka brokers was written correctly to like the correct file destination or file path. We have some other workflows within our control plane, such as workflows that will like create EBS volumes, delete out EBS volumes, etc. But these are like the main workflows that we use on a regular basis. And I'll talk a little bit more in depth about the planner workflow, the replace broker workflow, and the archive monitor workflow in a bit. So let's talk about these workflows. Let's start with the archive monitor workflow. So we have some workflows that we've added to our control plane that probably don't necessarily need to use temporal. However, this archive monitor one is a good example of where you'd want to have something that would utilize durable execution. So just to talk about it, to beat it to death, what the Kafka archiver does is we have all of our users writing their events to Kafka. We then write them to S3, and it's really important that when we write our data to S3, we do this in a timely manner. We have this batch job that runs on a 15-minute cadence that continuously consumes from all of our Kafka topics and then writes the data to S3. And it's important that it's there fairly quickly because there are a lot of downstream jobs that depend on this data being there within about an hour. So when this archiver, so like, just like painting a picture, we've had like file corruption, like one file being corrupted within like our S3 events bucket, and like this will cause like a major incident because the entire Airflow job that reads for maybe 1,000 different file paths, one file was corrupted, and then the entire Airflow job fails. And so it's really, really important that we're able to quickly determine whether there was some sort of issue when uploading the data to S3. So this is what we need the archive monitor for. So what is this workflow? It is a combination of both a parent and a child workflow. It starts off by running this thing called the archive monitor workflow, like I said, but then basically for every single file path that we're expecting to be created on the 15-minute cadence, we spawn a corresponding child workflow, and this is the actual logic that checks to make sure that this file was created correctly. This workflow also runs indefinitely, so because we're constantly like pulling data, it will every 15 minutes it will start however many child workflows it needs, and then it will wait 15 minutes when it will then spawn the child workflows again, and then basically continue to do this until we stop it manually. What these child workflows do is they check to make sure that these Kafka topic events were written to S3. So let's just paint a picture of how this works. So like I said, you have this parent workflow that on a 15-minute cadence spawns these children workflows. So it'll spawn the children workflow, go back to sleep, and then wait and continue to do this process again and again and again. The child workflow will then wait and check these S3 paths. So although we hope that that the data that was written to Kafka is written to S3 every 15 minutes on the dot, it's not realistic for that to happen. Like there's going to be some problems along the way. So this child workflow will kind of wait indefinitely until the path is created. And if the path is created, it's all good. It will everything business is normal. It will terminate. But if the path isn't created after a specific amount of time, depending on the topic, we have different thresholds. It will fail, and as a result, this will page us to let us know that that we need to go check to make sure why the archiver is not working correctly. So like I said, let me see. Yeah, so like I said, this workflow is a really good example for when you want to use durable execution, because you have these child workflows that are just spawned and kind of wait indefinitely, and they have to store the state of the specific file path for that topic, for that partition on that specific cluster. And these file paths are pretty long, and they're fairly unique for every topic, partition, and cluster. So it's useful to be able to store this data within a database so that you don't need to consistently respawn specific requests to check for the file path being created correctly. So this is like a really good example of when you'd want to use Temporal in your system. Another good example for when you would want to use Temporal would be our replace broker workflow. Our replace broker workflow, like I said, it replaces brokers, like you can assume, like you can imagine. And there's two use cases for when we want to replace a broker. The first use case is that the broker is just unhealthy. I don't know. We have we call the AWS API to check whether the brokers within our clusters are healthy. If they return that one of them isn't, then we want to go ahead and replace that specific broker. Another thing that we have to do is we have these various regulations that we have to abide by. I believe it's just law for payment for financial tech companies. I might be wrong, but on a 30-day cadence, we need to restart every single one of our hosts and then on a 90-day cadence, we have to replace each one of our hosts. And this was before my time. Like, we could have two different workflows. One that on the 30-day cadence just restarts the broker, restarts the host, my bad, and then one that replaces the broker, the host, on a 90-day cadence. But I think just to make it simpler, we just have one workflow that just replaced the host. So every 30 days, we're replacing every single host in every single one of our clusters, which is it's a pretty tall order. And so prior to the control plane, my teammates had to go ahead and do this operation manually, which if you have like hundreds of brokers, it can be really time consuming and toilsome. So the control plane relieved this burden. We now had a way that we could automate broker replacements, but the original implementation was pretty simple. All it would do, for example, let's say we're dealing with an unhealthy broker, it would detect that a broker was unhealthy. It would then make a call to AWS to terminate the broker within that ASG, and then it would spin up a new broker in its place. There's some more details, like you'd have to detach the EBS volume from the unhealthy broker and then attach it to the new broker that's being spun up. But the major issue with this was that because of the time it took to bootstrap the new host, it would take around 20 to 30 minutes. And because of that, your system would be in a state where you had under-replicated partitions for those 20 to 30 minutes, which is an issue. So to fix this, we came up with something called EBSM, which is an acronym for EBSM management. And the first thing that we had to do was we had to change how our clusters were set up. So basically for every single Kafka cluster, we just have the standard cluster. But then we also have a standby broker on the side it's already been bootstrapped correctly, and it's basically just waiting for a replacement to happen within the cluster, and then it'll get swapped in. So just to kind of go through it, let's say, again, we have another unhealthy broker. So before we actually talk about the EBSM swap, the EBS swap, let's diagram out what our brokers look like. So for every single host, we have 3 EBS disks attached to it. We have one for the operating system, one that contains all of the open source software that's being used on running that host, and then one that stores all of the events that are being written to that specific broker. And in this replacement step, we want to target the EBS disk that has all the Kafka data. So let's walk through how this specific replacement strategy works. So if you can imagine, we have an active broker and the standby broker on its side. So this diagram is correct. The standby broker does have an EBS disk attached to it. It doesn't really do anything, though. It's really small. It's 50 gigabytes. And the reason why we have to do it is because that's just how our infrastructure is set up at Stripe. Each host has to have some sort of instant storage associated with it. For this replacement to work, the first thing that we do is we go ahead and we detach the EBS disk from the standby broker, and then we do the same thing for the active broker. We then take the EBS disk from the active broker and we attach it to the standby. Once we do this, we kill the host that we want to replace, and we start the Kafka process on the standby broker, and then it gets selected into the cluster, and that's your replacement. We've seen good results with this. So as I mentioned earlier, it took about 20 to 30 minutes to get into a state where we didn't have under-replicated partitions. But with this EBSM replacement strategy, we were able to get this down to about 1.5 minutes, which is a 90% reduction, which is pretty good. I think that this is definitely a really good use case for Temporal because, like I said, you want to be able to maintain the state or manage the state for the specific processes. Like, let's say that you have an activity that fails after you detach the broker or the EBS volume from the standby broker. You want to make sure that you don't start the entire process again. It's nice to be able to retry that activity and keep going from there. This is definitely also a pretty cool way to replace your hosts. I'm just personally not that convinced of the merits of it. Don't tell my manager, but just because, I don't know, under-replicated partitions isn't really the end of the world, and if you can ensure that you're not applying other operations to the cluster at the same time, it doesn't really matter, in my opinion, if you have 20 minutes of under-replicated partitions. You really don't get into trouble until you have under the minimum number of in-sync replicas. So the engineering investment in order to get this to work was pretty significant. So I mean, it works and it's cool and now it's great. But to get to this point where it's stable in production, it was a really long road. So let's talk about how we automate all of these processes, because it's great that you have specific workflows you can run, but if an engineer has to go ahead and run them, you're not really saving on that much of the toil. So we have this Kafka planner workflow. And what does it do? Like I said, it replaces unhealthy brokers, as well as brokers that have exceeded their compliance time frame. It rebalances Kafka clusters, and it also replaces unhealthy EBS volumes. So I think I mentioned this earlier, but this workflow is running on a 15-minute cadence, and it basically just goes through and it prioritizes specific operations that it wants to run. So it takes both the cluster health as well as whether the cluster should be rebalanced. And then the priority goes as, if there's a corrupt EBS volume, the first thing that it will do is it will replace that EBS volume. Next, if a broker is unhealthy, it will replace that broker automatically. And then, moreover, if the cluster then needs to be rebalanced, it will go ahead and rebalance the cluster. So it prioritizes the operations in that order, and yeah, that's what it does. But there is a caveat. When you're running like all of these operations on your clusters, you have some that kind of need to work in tandem. It can be a little bit dangerous. So, because like imagine, for example, you replace a broker on your cluster, and then you also run a rolling restart, then you can get into a state in which you potentially are under the minimum number of in-sync replicas. So we have two strategies that we use to make sure that we don't apply operations to a cluster prematurely. The first one is a safety barrier, and the second one is this thing that we're working on, which is workflow coordination. So let's talk a little bit about the safety barrier. It's pretty simple. But what it is, it's like this workflow that we wrote that encapsulates any block of code. So all these specific workflows can utilize a safety barrier. You kind of just wrap all of your logic within the safety barrier workflow. And it's a verification system that requires like a Jira ticket approval. So before like the operation can be applied, it creates a Jira ticket. You then have to go and approve the specific Jira ticket, or you can cancel it. And depending on what you do, the workflow will either run or it won't. We use this for a couple of things. One is like when you're rolling out new features to the control plane. So for example, we had like a lot of problems with rebalances. I guess we still do, where we'll rebalance a cluster and all of a sudden like some of our users will see like increased latency. So when we were actually trying to automate rebalances, it was nice to be able to have this Jira ticket that would spin up and prevent the rebalance from being applied automatically. And then it would be nice to have like one of our teammates go ahead and then check to see whether the cluster could be rebalanced, like whether it wasn't like at a hot point during the day. For example, like midnight UTC, we have a lot of increased traffic. So we probably wouldn't want to have a rebalance run at that specific time. We'll also do things like turn traffic off to one of our clusters and then run a rebalance like that. So there's like a bunch of different things that you would want to do in this case. And yeah, so like I said, it applies additional friction. Another example of when we use the safety barrier is when users reduce their attention on their Kafka topics. We have the safety barrier prevent that operation from happening. so that we make sure that there's like no risk of data loss. So more of a pictographical, image walkthrough. Imagine that you spawn some workflow. You then go ahead, it then creates a JIRA ticket. Then you can either disapprove it or approve the operation, and it'll run like that. So at Stripe, we do all of our configurations through version control, which is I guess it's useful in the sense that you then have like a paper trail of every config change that you've made, but it's slightly annoying in a sense that like if you want to like repartition a topic, it takes a really, really long time. So the safety barrier is nice is because we have it feature flagged enabled, so it's really, really easy to be able to prevent a specific workflow from running when we don't want it to. So for example, like we've had a lot of incidents where broker replacements weren't really they were caused by like faulty broker replacements, like specifically with something like EBSM. So with the safety barrier, we can easily just go ahead and then turn off all automatic broker replacements, because you have to then go approve the ticket. So if we don't approve the ticket, then no broker replacements will happen. So this is a super nice feature to be able to like turn workflows on and off. Now let's talk about this new feature that we're developing for the system, which is concurrent, which deals with concurrent workflows. So I alluded to this earlier. We have like a lot of agents within the system now. We have the thing called Henson, which will apply Kafka configurations to clusters, and this requires a rolling restart to happen. Then we also have like the planner that's consistently trying to go ahead, check the state of the system, and then run operations like broker replacements. So I gave this example as well. You can get into a state where Henson is now trying to run a rolling restart on a cluster while the planner is trying to replace a broker in the cluster, which you really don't want to happen, because then you get into trouble with potentially falling under the minimum number of in-sync replicas. So the way that we did this previously to make sure, well, we kind of just hoped for the best, and it worked for a while. But one way to ensure that we ensured that multiple, for example, broker replacements weren't happening on a cluster at once is we used this idea of mutual exclusion through workflow IDs. So if you aren't very familiar with Temporal, every single workflow that you run has a workflow ID associated with it. And within a specific temporal namespace, you can only run one workflow that has that specific workflow ID. So what we would do is we would name our workflows with just two fields, the workflow type and the host type. So for example, for broker replacements, all of our workflows, all of our replace broker workflows that would replace a broker that belonged to the Kafka pub host type, we would call it replace broker Kafka pub. And because of this mutual exclusion, you couldn't run another broker replacement on that specific host type. And it works. It's a little primitive in a sense that if you have multiple clusters that belong to the same host type, you can no longer replace brokers on the other clusters, but it ensures that you're not doing multiple broker replacements on a specific cluster at once. So yeah, I mentioned this. So another issue with this this method is that you can still have other workflows run on the cluster. So the case with the rolling restart and the broker replacement still can happen, because the rolling restart is going to have a different workflow ID from the replace broker workflow. I mentioned this about you can only do one. You can only replace one host per host type, which is time consuming, or it limits the amount of the time in which you can actually replace the hosts. There's also little observability into what every workflow is doing. So Temporal has a nice UI and that you can open up, and you can go and see all the workflows that are running within your namespace. But if 90% of your workflows are called like replace broker Kafka pub, it becomes not as useful, because it's hard to filter down into which specific workflow is replacing which specific host. So what I'm currently working on is this project which we call workflow coordination, and basically what we're trying to do is come up with a system that will limit the number of operations that can be applied to a cluster to be one at a specific time. When designing this, we went through a bunch of different potential designs. We thought about using a queue. We thought about building our own locking system. At one point, we were talking about using a distributed locking mechanism, which was probably way too overkill. But we settled on using a locking mechanism that again uses mutual exclusion through workflow IDs. So the locking mechanism works in the following way. Let's say that you want to, let's say like you want to replace a host within a cluster. You start by running this specific workflow, the replace broker workflow. What you then have to do is you then have to acquire a lock on the cluster. And what this lock is it's going to be a child workflow that is run asynchronously in the background. That is the name of that specific cluster. So, for example, we have a cluster called Kafka Pub Northwest Jade. If you wanted to replace a broker on that specific cluster, you have to be able to start that child workflow before you go ahead and actually run the specific operation. Once you've acquired this lock, you can then go and finish the task at hand. And the way that we implement this, this is a little, this is simpler than what the actual implementation looks like. But imagine we have like two functions, one that's going to acquire the lock and one that will release the lock. What the acquire lock will do is it will continue to spin and spin and spin until it can actually acquire this specific workflow, until it can acquire the lock for the cluster, which is spawning that child workflow that has the cluster name in it. Basically then after it's finished its operation, we have a release lock function that it can use to kill the workflow. One thing to note about this is that if you're also familiar with Temporal, when you spawn child workflows from a parent workflow, you can give specific parent-child workflow policies, which basically say what you want the child workflow to do when the parent is done. You can either say like, hey, I want the child workflow to continue to run, and this is called like an abandon policy. Moreover, you can say that you want the child workflow to terminate. So something that we do to make sure that like this lock is always released after the operation finishes, even if like the entire workflow fails and you never get to the release lock function, is that we terminate that child locking workflow to make sure that there's never just a time where you have like a Kafka Pub Northwest Jade workflow running and no other operations can acquire that lock. So some closing thoughts. So Temporal is is really great for a state machine. You can have these really long running workflows that hold state. For example, the replace broker workflow or the archive monitor workflow. This makes it so that it's like deploy resistant, and with activity retries, you can make sure that your workflow picks up at the spot in which it failed instead of trying to re-execute the entire process. Some other takeaways. I think what I've realized recently is that working with temporal primitives can be difficult. They seem super simple, but there's really small nuances to each of them that make it that you may not be able to do exactly what you set out to be able to do. So, for example, when I was like building this locking mechanism, I thought it was going to be like 10 lines of code, take a day or two to implement, but it took a lot longer just because of the way that like child workflows work and how you can like ensure that the child workflow is started correctly. So, it was kind of annoying. The temporal UI is also really nice. It's really easy to go to be able to go in and see like which specific part of your process failed. So like for example, debugging something within the control plane I find to be much easier than debugging something with kproxy, which doesn't use temporal at all, because you get an error, and if the error is not very verbose, it can be very difficult to determine what part of kproxy failed. Some other issues with Temporal is that there's just tons of configurations that you have to set up when you are when you're defining these workflows. It can be kind of annoying. I think that some of our design decisions weren't optimal. For example, our topic configuration workflow probably didn't need to be within the control plane. That probably could have just been a cron job that's run. You don't really need to manage state there. And the biggest gotcha is that every single activity, the output is serialized to a database. So there's a 2 megabyte size limit that you have for the data that can be returned from each single activity, which a lot of people have problems with. I was at like a conference last year for Temporal, and yeah, there lots of developers did not like this. So as we continue to move forward, I would say that primarily my team's focus is going to be to continue to invest in the system as in comparison to other parts of the other services we manage. Ultimately, I think that the long-term vision would be to have something like Netflix has, where you can kind of go ahead to UI and spin up a cluster. But I would say in the short term, we're probably just going to invest in continuing to add operations that reduce toil to the control plane. For example, like adding and removing brokers. That would be useful. Moreover, like being able to use stateful repartitioning. Our repartitioning is pretty difficult because we want to ensure that there's no data loss depending on like what your reset offset policy is and you're on the consume side. So it would be great if we could make that a little more automated for our team. But yeah, that's the Kafka control plane at Stripe. Thank you for listening.